Hello, dear students. Today, in this lecture, I will discuss with you enantiomers and their properties. And what are the enantiomers? What are their properties? And how we can assign the configuration of two enantiomers, and which rule is applied actually for the nomenclature of the enantiomers. We will be discussed all the things in this lecture. And the learning objective of this class to understand the concept to assign RS nomenclature of two stereoisomers, especially the enantiomers, right? Means we will discuss the concept to give an nomenclature of to the enantiomers and understanding the 2D representation of the compounds. Okay, we will we assign the RS nomenclature to the compounds. In the 2D, first we draw the structure of the compound in 2D and we will assign the RS nomenclature to the enantiomers. And the learning outcome of this class, student would can do nomenclature of stereoisomers by getting the knowledge about these. From this lecture, student will be able to nomenclate the stereoisomers, and the student will be able to determine the correct configuration of stereoisomers that would be beneficial in asymmetric organic synthesis, right? So now the term stereoisomers, what do you mean by the stereoisomers, and enantiomers are also the type of stereoisomers, and what are the enantiomers? So these are the compounds which are non-superimposable mirror images of each other, and any molecule that is chiral must have an enantiomers, right? They must have an enantiomer if any molecule is chiral, right? So to understand the term enantiomers, we can easily understand this thing by using the example that is hand. When I will see this hand in the mirror, this is the mirror. I put here the mirror at the perpendicular. When I will see this in the mirror, it will look like this. In the mirror, it will look like this, right? And these hands are actually the mirror images of each other, right? And these mirror images are actually non-superimposable on each other. We can't superimpose this hand on this hand, right? Because here different groups, different fingers are the coming on the fingers of the first hand, right? So there is not completely superimposable of this image of this original molecule, right? These are the non-superimposable mirror images, and these are called the enantiomers, right? And this can also be understood by taking the example that is the compound. This contains the chiral center here. The chiral center means the carbon. This is the carbon. This carbon contains actually the all four groups are different, which are created with this chiral center. This center. So this center is called the chiral center, right? Chiral center is also called the actually the asymmetric center, right? We do not have the symmetric, right? Plane of the symmetry. So there is no plane of the symmetry, means plane cannot bisect this molecule into two equal parts. Two equal parts, right? So whenever I will see this compound in the mirror, this is the mirror. So when this will be seen in the mirror, then it will looks like this. Okay, and when I will the left this compound from here and put on this compound, then these groups these H and Br will they come at this side, and CS to CS will come at this side of this compound when I will impose this structure on this compound. So these mirror images are the non-superimposable on each other. Okay, so the non-superimposable mirror images are called the enantiomers. These are the enantiomer pair. They are the enantiomers of each other, right? Now talking about the chiral carbon atom. Before understanding the chiral carbon atom, we can't they assign the nomenclature to the enantiomers or to the stereoisomers. So chiral carbon atom is also called as actually the asymmetric carbon atom, right? And this asymmetric carbon atom has four different groups. This has four different groups. These four different groups are bonded with this chiral carbon atom. Here, this is the chiral carbon atom, and there are four different groups. This is green ball. This is green ball means green ball. These specific groups, and this is the blue. The or different colors balls means there are different groups attached with this chiral center, right? Whenever I will see this compound in the mirror, then it will look like this, right? And these are actually non-superimposable. Now, if you talk about these two centers, then asymmetric carbon atom is the most common example of the chirality center. So the chirality. What do you mean by the chirality? Chirality is the property of the compounds which contains the chiral center, right? So asymmetric carbon atom has also the chiral center. So the chirality center belongs to an even broader group called stereocenters. And a stereocenters or stereogenic atom is an atom at which the interchange of the two groups gives the stereo isomers. So this is the stereocenter. Actually, this is the center at which all the groups present are the different, and if we exchange two groups, position of the two groups, or you can say the orientation of the two groups, if we change, then they will convert. Stereoisomers will convert into each other, right? Only by changing the position in this case, we can convert one stereoisomer into its stereo isomeric pair, right? Now this is cyclic compound. This type of the stereoisomer, that is, it has the there is this is the cyclopentane ring. In this cyclopentane ring, there is one chlorine atom and hydrogen, and there is one chlorine atom and one hydrogen atom. So these same groups on these chiral centers, these chiral carbons, these and these. These hydrogens, same groups are present at the same side. Okay, so this compound, this type of the compound where same groups are present at the same side are called the cis compound, right? And if this compound contains, the internal mirror plane, this is the plane. Okay, when I will pass a plane to this compound, and if this plane will bisect this compound into two equal parts, then then even even they contain the chiral center, but these compounds will be, the optically inactive due to the presence of the plane, right? Due to the presence of the internal mirror plane. So this is compound, and this compound is actually the meso compound. This type of the compounds are called the meso compound, right? 6,1,2-dichlorocyclohexane is a chiral because the molecule has internal plane of symmetry. So overall, this compound. So even though this compound contains two chiral center, but overall this compound shows, you know, or overall this compound is a chiral. Why this is a chiral? Because these chiral centers have the plane of symmetry, right? There is plane of symmetry, and suppose in these two chiral centers, if this chiral center have the R configuration, then it will have the S configuration. So this the optical rotation of the plane polarized light by this center will be cancelled out because they are they will rotate plane polarized light in the opposite direction, right? Opposite direction and up to the equal extent, equal magnitude. So they will cancel out to each other. Overall rotation of the plane polarized light by these centers would be zero. That's why this compound is called a chiral. Both structures above can be superimposed. They are identical to their mirror images, right? They are identical. Now, if you talk about the transcyclic compound, uh, this is the trans compound. This does not have the plane of symmetry, and this does not also have the plane of symmetry. They are mirror images of each other. So, overall, these are actually the enantiomeric pair. These are the enantiomeric pair. Okay. This connected to chiral center. One is this, and second is this, and both the chiral center have the same configuration. Suppose this is D, this has D configuration, then it will also have the D configuration. So overall, this compound is the chiral compound. It will rotate the pendulous light. Trans 1 to dicyclohexane does not have a plane of symmetry. There is no plane of symmetry. This plane will cannot bisect this compound into two equal parts because the orientation of the groups in both sides, the orientation of the groups is different. Okay, so we can't say that the orientation of these or this plane will bisect these chiral centers in uh, in equal parts, in identical parts, because these parts are not identical, right? So the images are non-superimposable, and the molecules will have two enantiomers, right? Now talking about the RS configuration. So how you can assign the RS configuration to the compound? This is the compound natural alanine. This is the natural alanine, and this is not the natural alanine. And this is the mirror image of this compound. When I will see this compound in the mirror, then it will look like this. And this is natural alanine. This will found in the nature, while this will not found in the nature. So how we can assign the RS configuration to this compound? So both the enantiomer of the alanine receive the same name in the IUPAC system, 2-amino-propanoic acid. The IUPAC name of this compound is the 2-amino-propanoic acid. Okay, but the prefix used before the IUPAC name of this compound will be different. If one has the R configuration, R prefix, then second may have the S configuration. Right? This is due to the presence of the groups in different ways. So we can say their orientation in the space are different. Only one enantiomer is biologically active. In alanine, only the enantiomer on the left can be metabolized by the enzymes. So this natural alanine, this is biologically active, and this can be metabolized by the enzymes. This enzyme will react with this compound, this enantiomer, while not with this enantiomer, right? And enzymes can metabolize, can consume this enantiomeric, right? A way to distinguish between them is to use stereochemical modifier ROS. So actually to distinguish these compounds, these pairs, we have to assign configuration stereochemical modifier before the name of these compounds. So to assign the nomenclature to the enantiomers, Kahan, Ingold, and Kellogg have given a rule that is called priority rule. And according to the priority rule, we assign the numeric priority order to the groups which is present with the or connected with the chiral centers. So enantiomers have different special arrangements of the four groups attached to the symmetric carbon, and the two possible special arrangements are called configurations. Each asymmetric carbon atom is assigned a letter R or S based on its three-dimensional configuration. Each asymmetric carbon atom actually assigned a letter R or S, and it will depend upon the three-dimensional configuration of the groups. Current Ingold and Pillow convention is the most widely accepted system for naming the configuration of the chirality centers. And according to the Carningod and Pillow, that is called in the sorts CAP rule, right? So according to CAP rule, First, we assign a relative priority to each group bonded to the asymmetric carbon. Group 1 would have the highest priority and group of second, etc. And these priority to these groups, priority order to these groups is given on the basis of their atomic number. At the atomic number, priority would be higher of the groups, right? So here, this is the series of the priority order, and iodine has the most. This is the most priority group. It is the greater priority to that of the high priority, that of the bromide, and this is how the greater high priority than the chloride, higher than this sulfur that is high priority than fluoride, and hydrogen means protium has the lowest priority, and this deuterium has the higher priority than the H1. Okay, so on the basis of if we move from left to right, so the right to left, then you will see that the atomic number of these compounds, these elements is actually in the increasing order, right? Now we will assign the priority to the groups. Just a moment. So we will assign the priority to these groups. There is carbon, chiral center, hydrogen, there is CH3 methyl group, this is fluoride, this is NH2. If you talk about the directly connected atom of the group with chiral center, then there is carbon, there is fluorine, there is nitrogen, there is hydrogen. If we talk about the atomic number of the fluoride is greater than the nitrogen, and it has the atomic number greater than the carbon, and it has the greater than hydrogen. So first prior group would be the most atomic number containing groups, that is fluorine. And second priority group is the ammonia, and third priority group is the CS3. And last least priority group is the hydrogen. Okay. There is it is very easy here to assign the priority to these groups on the basis of atomic number, right? So this is the priority order. And after giving the priority to the groups, we will move in the sequence. First to second, and second to third, and third to fourth, fourth priority group. So our movement here, we can see easily that our movement in the sequence 1, 2, 3. This is our movement. 1, 2, 3. This is our rotation, right? In the sequence. So this is the sequence. This sequence is the anticlockwise. This is the anticlockwise sequence. Or we can say anticlockwise rotation. So our rotation, when we move from first to second to third priority group, then our rotation would be anticlockwise. So according to the anticlockwise rotation, the configuration assigned would be S. S means sinister. Sinister means left hand side or anticlockwise. Right. Now R and S configuration, breaking ties. In case of ties, use the next atoms along the chain of each group as tiebreakers. Suppose we have this type of the group, this type of the chiral center, right? Here is the chiral center, hydrogen, hydrogen, bromine, chlorine, chlorine, hydrogen, CH3, 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 CH2, yeah, right? These type of the groups we have, and CH2, 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 CH3. Suppose these groups are attached with the chiral center, right? So these all have the carbon atom, right? So if these four groups are attached with the chiral center, then we cannot assign their priority on the basis of first atom. It is directly attached with the chiral center, right? So we have to move ahead at the second position, and at the second position there is bromine atom, and here at the second position there is fluorine atom. Fluorine atom. At this side CS3, there is CS3, CS2BR. CS3, CS2BR. Right? So from these four groups, this group is the first prior group because at the second position there is most atomic number containing bromine. Okay. Then second prior group is this because there is chlorine atom at the second position, and there is CS3, 3 CS3, while there is only 2 CS3 groups and hydrogen. So this will be the third prior group, and this will be the fourth prior group because there are only 2 CS2. There is 3 CS3, right? So on the basis of the second position of the at the second position, atomic number of the groups at the second position, we can assign the priority order to these groups, right? And this is the least priority because there is only one alkyl groups with this carbon. This first position carbon, there is only one alkyl. This is the least priority. Now, if treat double bond and triple bond as if each were a bond to a separate atom. So if there is double bond or triple bond, then treat these as the separate atoms. For example, break and duplicate. Right? This is the compound. With this compound, there is double bond. If we break this double bond, then there will be a single bond here, sigma bond, and there will be also be a new sigma bond like this. Suppose this is the new groups after breaking the pi bond and formation of the new sigma bond. So there are two carbon-carbon. So means if we are talking about this center, so with this center, two carbon atoms are attached. Double bond means two carbon atoms are attached with this carbon. Like this. With this carbon, two carbon atoms are present. One is this, and second is this. And with this carbon, there is double bonded carbon is there with this carbon. So this carbon has also two carbons. One is this, and second is this. Okay. So double bond and triple bond we treat as separate atoms. Right? There is also two carbon atoms attached with this nitrogen. So double bond means two carbon atoms, right? One is this and second is this, right? Now, RNS configuration is step number 2. So, working in 3D, rotate the molecule so that the lowest priority group is that remains in the backside. So, this is the one, this is the compound, this is the first priority group, second, third, and fourth priority group. So, here this group is actually in the plane, or we can say this is not backside. So, first we rotate this molecule in such a way that this fourth priority group or least priority group goes into backside. So here in this is this the comes now at the backside, right? And then uh, assign priority to the groups. Sorry. After assigning the priority to the groups, we will rotate this molecule in such a way that this priority groups goes back, and after that we will move in the sequence first to second and second to third priority group. So when we move from first to second and second to third pi group, then in this case, our rotation is actually the clockwise. So if we are moving in the clockwise direction, in the clockwise rotation, then the configuration assigned will be R. This rectus. Rectus means right hand side of the clockwise, right? So draw an arrow from highest to second highest to lowest means third pi group. And if our rotation for the arrow is clockwise, then the configuration assigned to the compound would be R. Or if the rotation is counterclockwise, then configuration assigned would be S, right? Now, assign the priorities to this compound. Here, this compound, this is the chiral center. At this chiral center, there is carboxylic group. Carboxylic group COOH, C double bond O and OH. There is only CH3. There is NH2 group. So if we talk about the directly connected atoms with this chiral center, this is the most atomic number containing group, NH2, nitrogen. So it will be assigned first priority, and the second priority assigned with this to this because there is carbon and here is also carbon, but with this carbon there is oxygen atom is present. But here with this carbon only hydrogen atom is present, which are having lowest atomic number, right? So this carbon will be given second priority, and this carbon will be given third priority, and hydrogen will be given fourth priority. So once we assign priority, we will move from first to second and second to third priority. So our moment is this. Our rotation is this. Anticlockwise, first to second and second to third, and then third to fourth. So rotation is here actually the counterclockwise. So the configuration assigned would be as sinister right. So this is the S aligning, structure of the S aligning. Now draw an arrow from group 1 to 2 and 2 to 3 to group 1. Ignore group 4. Clockwise R and counterclockwise S. Now, if I want to give the RS configuration to this compound, then first I will assign the priority. This is the first value, OH, oxygen, which is most atomic number containing group. Okay, this will be assigned first priority. Second priority group is CH2, CH2, CH3. Third priority group is CH2, CH3. Now everyone can easily assign, they can assign priority to these groups on the basis of the atomic number of the directly connected atoms with the chiral center. If we can't assign, if the groups are same, at the first position the elements are same, atoms are same, then we will move to the second position. Okay, and at the second position, if the the atoms are different, then we can assign easily priority. But if at the second position there are also the identical atoms, then we will move to the next position and we will assign the priority with the groups. So here the first priority is this and second priority is this. This is also CS2 group, this is CS2 group. So can't assign the priority on the basis of first. But at the second, there is CS3. Can't assign the priority on this. But at third position, there is CS3, there is only hydrogen. So this will be most prior than this. More prior than this, right? So priority will be given as first to second or second, third. And this hydrogen in this compound is actually at the above side of the plane or towards V1. Towards V1. So, but rule is that to assign the normal to configuration to the compound, we they put this hydrogen or the least paired group at the back side of the tank. So we will rotate this compound so that this will move to the side, right? This like this. So we have rotated this compound and here these only these groups are interchanged. These groups, this is same, its position is same. These groups are portion of these groups are interchanged. Okay. So there is the I mean I have kept CH2 CH2 CH3 groups and rotate this molecule like this. This is suppose CH2 CH3 CH3 groups. Second bracket. Okay. This is hydroxide group. This is I'm watching this compound from this side, my side. Okay. So this is front hydrogen. This is CH2 CH3, right? So I will rotate this compound in such a way that this hydrogen move to this side, right? This gives now back side from me. Okay. And this is hydrogen CH2. So this is there is hydroxide group, there is CH2 CH3 group, and there is hydrogen. Okay. So when this compound by 120 degree, then this type of orientation will be up here, right? And now I will assign configuration to this compound. So this is first by group, second, third, and fourth. So there is only clockwise rotation of this. Clockwise rotation. If there is clockwise rotation, then we will assign the R configuration to this compound. So when rotating to put the lowest priority group in the bed, keep one group in place and rotate the another three groups, right? So our rotation is actually clockwise. So rotation will be R. Now examples continues. This compound would give as configuration because this is the first paragraph, this is second, this is third. Now this is actually this is four carbon containing chain. This is four carbon containing chain, but in this chain, this carbon is connected with this group by double bond. Means with this carbon, two propyl groups are present connected. Means right. While in this with this CH2 group, only propyl group is present connected. Right. There is two propyl groups connected with this carbon, so this will be more pair group than this. This will be more, first pair group. This is second, and this is third, and this is fourth. So we will move from first to second and second to third. Our rotation is actually the clockwise or the counterclockwise. So the configuration will be assigned as right. Now configuration in cyclic compounds. If you talk about the cyclic compounds, then in this compound actually this is the ring, and ring is we consider the ring in the plane, right? So these groups are present in the ring, right? And this hydrogen is present back side of the plane, and this is front side of the plane, right? If you talk about the parity, if you assign the parity to these groups, this is most pair group because here with the carbon, two carbon atoms, three carbon atoms are present. Well, there is one carbon atom. With this carbon atom, only one carbon atom is present. And with this carbon atom, there is only one carbon atom is present. Okay, so this is the more pair group, most pair group. And if you talk about the second and third, these carbon atoms, then with these centers there is one carbon atom, there is also one carbon atom. But with this carbon atom, there is doubly bonded carbon and there is doubly bonded oxygen. So oxygen has the more atomic number than the carbon. So this will assign second priority and this will assign third priority. Means this is more priority than this, right? And after assigning the priority, I will move from first to second and second to third pair group, and our moment is actually the counterclockwise. So the assigned configuration will be as right, and this can we can explain this easily, by the drawing its structure by opening the bonds. Okay, clearly we can assign. Now Properties of the enantiomers. Enantiomers have the same boiling point, melting point, and density, and same refractive index they have. But they rotate the plane polarized light in the same magnitude, but in the opposite direction. Okay. So except their optical property, enantiomers have the same properties like boiling point, melting point, density, refractive index, etc. So different interaction with the other chiral molecules. They have different interaction with the other chiral molecules because chiral molecules have the specific orientation of the groups. Okay, so specific orientation of the groups have the selectivity for interaction with the other molecule, right? Just like the key lock theory, a specific type of the key will fit in the specific type of the lock. Like this, a specific type of the enantiomer will interact with the specific type of the chiral molecule, right? So the test but active site of the enzyme is selective for a specific enantiomer, right? In our body also, this is also the concept working in our body, right? That if we take receiving mixer in the form of drug, then only one enantiomer from the receiving mixer will interact with our body. Okay, so we can say that one enantiomer would be the desired enantiomer to treat the disease in our body, while the other may be unreactive or may react, but in different magnitude, and maybe it can show side effect, right? Taste buds and scent receptors are also chiral, and enantiomers may have different smell. So enantiomers in our body also have different smells because our taste buds are actually different. How the selectives? They have the chiral centers. Now these are the reference books. PDF link. If you copy this link and paste on Google, then you can shine. You can easily get the PDF of these books, right? Now the multi-choice questions. The first question is, what is full form of CIP? So CIP means can infrapolar, no. Can indigo purple, no. Can ingold yellow, yes. The full form of the CIP is the can ingold and yellow. And the option chiral ingold and long, no. Option C would be correct option, right? And question number second, syn and anti nomenclature system is used for. So for what syn and anti nomenclature system is used? For enantiomer, for major compounds, for residual mixture of the enantiomer, for oxygens. So for oxygens, actually we use syn and anti nomenclature system, right? For enantiomers, we use RS nomenclature system, DL nomenclature system, capital DL and small DL also. For major compound, RS nomenclature we assign. Residual mixture of the enantiomer we assign RS configuration. And the question number third, what will be the configuration of major compound when S2 phenylpropionaldehyde reacted with Grignard reagent where CH is front side? Okay, so we have discussed this is already in the slides. Then the configuration of the major compound would be, if CH is front side, then configuration would be 2R3R, right? And if question number 4, what will be the configuration of major product when R2 phenylpropionaldehyde reacted with Grignard reagent where CH is front side? This will be 2R3R, right? Sorry, yeah, 2S3S. And what will be the configuration of major product when S2 phenylpropionaldehyde reacted with Grignard reagent where CH is present backside? So this will present backside, then the configuration would be 2S3R, okay? Means major compound formed will be 2S3R, right? And the question 6 is, chiral centers are present in glyceride So how many chiral centers are present in the glyceraldehyde molecule? So option number A, 1, B, 2, C3, and D4. So actually in the glyceraldehyde only one inch chiral center is present, right? Question number 7. Assign a relative priority to each group's bonded to the asymmetric carbon atom. So according to the atomic number, we can assign the priority to the groups. So in this order, this is fluoride. Fluoride is the most prior group. This is most prior group because it has the highest atomic number. This is more prior group than sulfur, and sulfur has more prior group than the fluorine. This is more prior group than the oxygen because they have the atomic number in the same order, right? Which is incorrect statement for allenes. In case of allenes, allenes are organic compounds in which one carbon atom has double bonds with each of its two adjacent carbon centers, right? Allenes are classified as commutative dienes. Allenes are classified as non-commutative dienes. And the parent compounds of the class is propadiene, which is itself also called allenes. So actually, allenes contains double bonds, concentrated double, the double bonds at the adjacent positions, right? So means they have cumulated double bonds. Allenes have cumulated double bonds. So allenes are classified as cumulative dienes, right? And parent compound of this class is actually protodiene. This is also correct option. So the correct statement. Allenes are organic compound in which one carbon atom has two double bonds. This is also correct. With each of its two adjacent carbon centers. So the incorrect statement is this. Allenes are classified as non-commutative double bond because allenes contains actually the commutative double bonds. So C option would be the correct option. Now question number 9, which is incorrect statement for enantiomers? They have same boiling point, melting point, density, and same refractive index. This is correct. Rotate the plane polarized light in the same magnitude but in opposite direction. It is also correct. And they have some interaction with other chiral molecules. This is incorrect because with the chiral molecules they have the different interactions. And the D option, active site of enzymes is selected for a specific enzyme. This is also correct, right? So only C option is incorrect option. Incorrect statements. Incorrect statement. So it would be correct option, right? Correct answer, right? Okay. And the question number 10. For RS nomenclatures, working in 3D, rotate the molecule so that the lowest priority group is in. So if we are doing RS nomenclature in 3D of the molecule, 3D structure of the molecule, and if highest priority group is actually coming towards Vihar or above side of the plane, then we have to rotate the molecule in such a way that the lowest priority group is adjusting backside. So option B would be the correct option. Backside, right? Not in the front side, not in the plane, not both red back. This is also incorrect because actually one group can at a time exist in only one plane, right? Either in the above side of the plane or in the below side of the plane or in the plane, right? Thank you. So if you have any type of the question, doubts, any queries, please ask to me. I would be very happy to answer you. Okay. So thank you again for listening me patiently. Thank you. Thank you very much. Have a good day.